The most beautiful thing we can experience is the mysterious. It is the source of all true art and science. That's Albert Einstein. And that sense of mystery, that drive to understand, is exactly what we're digging into today. We've got some source material here unpacking a real puzzle in particle physics, decades old, actually.
About a fundamental particle, the muon, and this weird wobble it does.
Right. We're looking at some really recent results, experimental and theoretical, focusing on something called the muon's anomalous magnetic moment.
Or G-2, as physicists usually call it. Basically how muons, which are like heavier electrons, act like tiny spinning magnets.
Yeah, and the way they wobble in a magnetic field, that's the key. For years, like decades, the measurements of that wobble just didn't quite line up with what our best theories predicted.
A small difference, but, a really stubborn one. And that got people thinking, maybe there's something else out there, new physics.
Exactly. It was this huge hint, maybe a crack in our understanding the standard model. But the sources we're looking at today suggest, well, maybe the mystery is solved.
But perhaps not in the way everyone expected. It looks like it came down to incredibly precise work, both in the lab and, crucially, in the calculations.
So our mission for this deep dive is to unpack how this happened. How did they resolve it? What does it mean for the standard model? And are there any loose ends?
And this is really cutting-edge stuff. Understanding these fundamental physics breakthroughs is, it's important for staying informed about where science and technology are heading.
Absolutely. Useful for general knowledge, maybe even if you're preparing for exams covering current science topics. It's about the building blocks of everything.
Okay, so let's start with the basics again. The muon's anomalous magnetic moment, G-2. Why focus so much on this specific property?
Good question. So, super simply, a particle like a muon should have a magnetic strength factor, G, of exactly 2, like textbook simple.
But quantum mechanics throws a spanner in the works.
Right, the vacuum isn't empty. It's full of these virtual particles popping in and out of existence all the time.
Like a quantum foam.
Exactly, and these virtual particles interact with the muon just for a fleeting moment, and that interaction changes its magnetic moment just a tiny bit away from 2. That tiny difference is the anomalous part, the G-2.
And here's the critical bit. Because muons are heavier than electrons, they can interact more noticeably with potentially heavier unknown virtual particles that might be lurking in that quantum foam.
So the muon's G2 is more sensitive to new undiscovered stuff than the electron's G2 is.
Precisely. It's like a more sensitive probe for physics beyond what we currently know. A window, potentially.
And this whole story, this discrepancy, it kicked off around 25 years ago, didn't it? The sources mention an experiment at Brookhaven National Lab.
That's right, Brookhaven.
Yeah.
Around the year 2000, the results first showed that the measured G2 value seemed consistently a little bit higher than the theoretical prediction at the time. That really generated buzz.
That was the initial hint, that slight excess, and theorists jumped on it trying to figure out what could possibly cause it.
Yeah, what known particles, or maybe even unknown ones, could add just that little bit extra to the muon's magnetic wobble? The anticipation for a better measurement, a more precise one, just grew and grew.
Which brings us to the more recent experimental work, the Muon G2 experiment at Fermilab. This thing sounds incredible.
Oh, it is a massive undertaking. They store muons in this giant 50-foot superconducting magnet ring and measure their wobble, the precession, with just insane precision.
How precise are we talking?
The sources say the uncertainty is just 127 parts per billion.
Yeah.
That's tiny. Like measuring the Earth's circumference accurately to within less than an inch.
Wow.
One of the scientists quoted just said, flat out, we have done it. Captures the feeling, I think.
And importantly, the result basically confirmed the older Brookhaven measurement, right?
Yes, remarkably consistent. So the experimental side looks solid. 2 different experiments, years apart, getting essentially the same answer for G2. An answer that was still stubbornly different from the old theoretical prediction.
Okay, so if the experiment held firm, the resolution, the change, must have come from the theory side.
Exactly. This is where it gets really interesting and quite complex. Calculating the theoretical value for G-2 is monstrously difficult.
Because of all those virtual particle interactions.
Precisely. You have to account for everything the standard model says can interact with the muon electromagnetic force, weak force, strong force contributions.
And the sources say the strong force part was the real headache.
That's the one, the contribution from virtual quarks and gluons popping into existence as hadrons particles made of quarks. That part is called the hadronic vacuum polarization, or HVP.
HVP. Got it. Why is that bit so hard to calculate?
Because the strong force behaves in really complicated nonlinear ways at the energy scales relevant here. So historically, the best way to estimate this HVP contribution wasn't purely from theory.
Oh, how do they do it then?
They actually relied heavily on experimental data from completely different experiments, ones where electrons and positrons collide and produce those hadrons.
Huh. So they used results from electron-positron smash-ups to figure out a piece of the muon's wobble calculation.
Sort of, yeah. By looking at how often hadrons were produced at different collision energies, they could infer the HVP contribution needed for the muon G2. It was a data-driven approach for that specific piece.
That sounds a bit indirect. Does that make it vulnerable?
It did introduce a dependence, yes. And that's exactly where the problem cropped up recently. A new experiment in Russia called CMD3
Okay.
at the VEPP 2000 collider. They published their results for those electron-positron collisions, and their findings disagreed pretty significantly with the older experiments that had been used for the G2 HVP calculation.
Whoa, so the data they were feeding into the theory was suddenly in question because a new experiment got a different answer for those collisions.
Exactly. Big wrench in the works. Which data set do you trust? The old ones, the new CMD3 result. It made that data-driven approach for the HVP terms suddenly unreliable, or at least highly uncertain.
So they needed another way, a way to calculate that HVP term without relying on this conflicting experimental data.
Precisely. And that's where the other big development happened. On the pure theory side,
Which involves
lattice quantum chromodynamics.
lattice QCD.
Lattice QCD, okay, what is that? Sounds complex.
It is. QCD is the theory of the strong force, quarks, and gluons. But calculating stuff with it directly is super hard. Lattice QCD is a computational technique. It basically breaks down space and time into a grid, a lattice.
Like graph paper for reality.
Kind of, and then it uses powerful supercomputers to simulate how quarks and gluons interact on that grid, following the fundamental rules of QCD. It lets you calculate things from first principles directly from the theory itself.
So instead of using the electron-positron collision data, they could try to calculate the HVP contribution directly using these massive lattice QCD simulations. That's the idea. And the CMD3 results really lit a fire under the theorists to push these lattice QCD calculations forward. Aida El-Qadra, a leading theorist, was quoted saying it became a very urgent thing that the community is taking seriously.
Makes sense. They needed a reliable alternative, fast.
Yeah, and multiple independent groups worked incredibly hard on this, using different lattice setups and techniques to cross-check each other.
And the result? What did lattice QCD predict for that hadronic contribution?
This is the punchline. The sources confirm it. When you take the HVP value calculated using these state-of-the-art lattice QCD methods and plug that into the overall standard model prediction for the muon's G2,
Yes.
it matches the experimental measurement from Fermilab. The prediction and the measurement now line up.
Wow. So the discrepancy wasn't new physics after all. It was that the previous theoretical calculation, the one relying on the older experimental data, wasn't quite right, specifically in that HVP part.
That seems to be the case. Once that HVP term was recalculated using the first principles lattice QCD approach, the tension between theory and experiment dissolved.
As physicist Pupeldev put it, another triumph of the standard model.
Indeed. A bit bittersweet, perhaps, for those hoping for definitive signs of new physics beyond the standard model.
Right. All those theories cooked up over 20 years to explain that specific difference between the old theory and the experiments. Dev said they're basically nixed now.
It really reinforces just how powerful and accurate the standard model is, even when pushed to these incredible levels of precision.
Okay, so the main mystery seems resolved. Standard model holds firm. But you mentioned loose ends. The sources suggest it's not perfectly tidy.
Right. Because remember why they leaned so heavily on lattice QCD? It was because the CMD3 experiment disagreed with older experiments measuring those electron-positron collisions.
Ah.
That disagreement still exists. We don't know why CMD3 got a different result for hadron production compared to the older experiments. Is there some subtle issue with one of the experiments? Or maybe there is some subtle physics going on, specifically in those electron-positron collisions, that doesn't directly affect the muon G2 in the same way.
So the puzzle that triggered the switch to lattice QCD is itself still unsolved?
Exactly. That discrepancy needs to be understood. So physicists are pushing on multiple fronts, refining the lattice QCD calculations even further, and also running new electron-positron collision experiments to get more data and try to clarify that situation. El Khadra stressed the urgency here, too.
It really highlights the interplay, doesn't it? Experimental results push theory, and advances in theory help interpret experiments.
Absolutely. And it shows the rising power of lattice QCD. It's not just for calculating proton masses anymore. It's becoming a crucial tool for high-precision tests of the standard model.
El Khadra had that nice analogy, didn't she, about the theoretical gardens.
Yeah, the well-established garden of results, often relying on some experimental input, and now the lattice QCD garden being in full bloom. It's matured into a really powerful first principles approach.
It's a great example of the scientific process. A persistent question, better experiments, better theoretical tools, and eventually, hopefully, clarity.
Though sometimes the clarity reveals new, smaller questions along the way.
So, connecting this back to you, our listener, why track this seemingly obscure particle wobble?
Well, fundamentally, it's about understanding the basic rules of our universe. How do the elementary particles behave? What forces govern them? This was a major test of our current best understanding.
And seeing how scientists tackle these fundamental questions using incredible technology and sophisticated theory, that's relevant for anyone interested in the progress of science. It's a prime example of a significant current development, the kind of thing useful for general awareness or even for, say, keeping up to date for competitive exams focusing on science and tech.
It really shows science as this ongoing process, decades of work, international collaboration, pushing boundaries, refining understanding.
Okay, so let's quickly recap this deep dive. We started with this long-running mystery, the muon's anomalous magnetic moment, G2, where experiments consistently showed a value slightly different from theoretical predictions, hinting at new physics.
Then, a super-precise new experiment at Fermilab confirmed the experimental value, making the discrepancy even sharper against the old theory.
But the breakthrough came from the theory side. A problematic piece of the calculation, the hadronic vacuum polarization, HVP, which previously relied on conflicting experimental data,
Was recalculated from first principles using powerful lattice QCD simulations. And this new calculation brought the standard model prediction into agreement with the experimental measurement.
resolving the main tension and marking a big success for the standard model.
But we also noted the lingering puzzle. The disagreement between the different experiments, like CMD3 versus older ones, that measured the inputs for the old HVP calculation still needs to be understood.
Which leaves us with a final thought to chew on. Given that the CMD3 data issue isn't fully resolved, and the current agreement hinges on the lattice QCD result, does that underlying experimental tension maybe hint at subtle complexities still hiding somewhere? Or is it purely an experimental measurement issue that will eventually be sorted out?
And looking ahead, now that lattice QCD has proven so effective here, what other deep mysteries in particle physics might it help unravel next? It feels like each layer we peel back reveals another fascinating layer underneath. The journey continues.
This is exactly the kind of complex but important current topic these deep dives aim to unpack, helping you stay informed.
We really hope walking through this nuanced story was valuable for you.
If it was, do consider liking and subscribing. It really helps us continue making these. And please, leave your thoughts or questions in the comments. Did anything particularly stand out? Are there other science or tech topics you'd be interested in exploring?
Engaging with these fundamental developments is, we think, really worthwhile, whether it's for formal study, exams, or just understanding the amazing universe we live in.